Whether you're a bioprocess engineer hunting for the perfect scaled-down model, a biotech founder architecting the leap to commercialization, or a scientific analyst who craves raw technical truth, you've reached the technical edge. In this space, we live by a single mantra: the process is the product. Welcome to the Biomanufacturing and Fermentation Technology podcast with Prasad Ernala. Hit subscribe and ring the bell to join a global community and stay at the vanguard of biotech translation. Let's build the bioindustrial future together.
Quantum fermentation.
It does make you pause for a second, doesn't it?
It really does. It sounds like the ultimate buzzword salad. You know, like something a startup founder pitches right before they run out of money. We're pivoting to AI-driven quantum fermentation on the blockchain.
I know exactly what you mean. It just triggers every skepticism alarm you have.
Yeah.
And, it should. Because usually when you see quantum slapped onto a biology topic, someone is about to sell you, like, magic water.
Exactly, or healing crystals. But, and this is why we're doing this deep dive, the stack of research we're looking at today isn't selling anything like that. It's not science fiction. It's a surprisingly gritty industrial look at a very specific problem.
Right. How do we make microbes make more stuff?
And more than that, it asks this really fundamental question that connects biology and physics. Can we actually engineer the quantum behavior of atoms?
Specifically something called tunneling.
Right, tunneling, to break through these biological ceilings that are, capping our industrial yields.
And we should probably set the stage right now if you're listening and thinking we're about to talk about telepathic yeast.
Or some kind of microbial hive mind that communicates across the tank.
Don't worry. The answer is a hard no.
But the reality of what's happening inside the cells is, I would argue, way cooler than the sci-fi version.
Oh, because it's real.
Mm-hmm.
Our whole mission today is pretty clear. We have to separate the woo, right?
Yeah.
The mysticism from the actual work.
We need to draw a line between these broad, kind of indefensible claims and what the source material calls mechanistically defensible science.
Exactly. And that defensible science has some heavy ideas.
Yeah.
We're talking kinetic ceilings, barrier widths, isotopic effects. So let's just ground this for a second. We're talking about fermentation.
The oldest biotechnology in the world.
Making beer, bread, you name it. You put yeast in, they eat sugar, they make a product.
And for centuries, when we thought about the limits, why the yeast stops working, we assumed it was a biological problem.
They ran out of food.
Or they poisoned themselves with their own waste.
That's the classical view.
Yeah.
And that's how we've optimized the industry for decades. Yields low, give them more sugar, genetically engineer them to be tougher. We just treated the cell like a black box.
Better inputs, better outputs.
Right. But the research we're looking at argues that we're hitting a totally different kind of wall.
Not a biological wall.
No, a physics wall. They call it a kinetic ceiling.
And that's a huge shift in perspective, right?
It is. I mean, think about it. You can give a microbe infinite food, the perfect temperature, remove all the waste. But at the end of the day, life is chemistry.
And chemistry is made of individual reactions.
Exactly. An enzyme has to grab a molecule, do something to it, like move a hydrogen atom, and then let go.
And that takes time.
It takes a non-zero amount of time. There is physical speed limit for how fast that enzyme can cycle.
It's like having a Ferrari engine, but you're stuck in a school zone. The car can go fast, the tank is full, but the laws of physics are the speed limit.
That's a perfect analogy. And the traditional biotech solution was just brute force. Make more enzymes. If one is too slow, just force a cell to make 10,000 of them.
Like adding more lanes to the highway.
But you run out of space.
Yeah.
You hit the law of diminishing returns hard. The sources call this allocation limits. A cell is an incredibly crowded place.
It's packed.
Totally.
Yeah.
You can't just keep stuffing more machines in there without breaking something else. It's like trying to fit 100 mechanics into a one-car garage. Nobody can move.
So the cell runs out of real estate, and the bottleneck just shifts somewhere else.
It always shifts. Maybe you run out of energy, or you hit thermodynamic limits, or maybe, and this is the key for today, you're just waiting for the reaction itself to happen. You're waiting for that molecule to get over the energy hill.
Which brings us back to physics. If the problem is how fast can a molecule react, we're not in biology's territory anymore.
And now we're in the jurisdiction of atomic physics, which brings us to the quantum lens.
Okay, before we go there, we have to clear the air. Because I did a quick search for quantum biology before reading these papers, and wow.
Interesting is a very diplomatic word for it.
I mean, I saw claims that microbes use quantum entanglement, This idea that bacteria are like instantly communicating with each other across the tank.
A quantum hive mind.
Yeah, to coordinate their eating habits or something.
And we need to be really clear. Our source material just flat out refutes this. It is almost certainly impossible.
Why, though? Entanglement is real, right? We build quantum computers with it.
Oh, it's absolutely real. But think about where we keep those quantum computers. They're in these giant refrigerators, cooled to almost absolute zero, in a perfect vacuum, shielded from everything.
And a fermentation tank is not that.
A fermentation tank is what physicists call warm, wet, and noisy. You've trillions of water molecules just crashing into everything constantly. It's a mosh pit.
And that creates something called decoherence.
That's the enemy of quantum states.
Yeah.
The environment just destroys those delicate quantum connections in like nanoseconds.
So the idea that one microbe could send a coherent signal to another.
The physics just doesn't support it. The noise is way too loud. It's like trying to whisper to someone a mile away during a heavy metal concert.
Okay, so no psychic yeast. We can rule that out.
No psychic yeast.
So if entanglement is off the table, what's the real quantum effect we're talking about, the mechanistically defensible one?
The effect we're looking for is tunneling,
Mm.
specifically hydrogen tunneling.
Right. Okay, let's break this down. In high school chemistry, they teach you the ball and hill model. For a reaction to happen, you need enough energy to push a boulder up a hill so it can roll down the other side.
That's the classical model. You need that activation energy. If you don't have enough, the boulder just rolls back. No reaction.
But quantum mechanics says tiny particles, like a hydrogen atom, aren't just solid balls, they're also waves.
The wave-particle duality, exactly. And this is where it gets weird. A wave doesn't have a precise location. It's kind of smeared out.
Yeah.
So part of your hydrogen atom's wave is on one side of that energy hill, and part of it might already be on the other side.
So instead of climbing the hill, you just appear on the other side.
If the energy barrier is thin enough, yeah, there's a non-zero probability that the particle just tunnels right through it. It bypasses the energy requirement completely.
It's cheating the system.
It's a shortcut.
Mm.
And because hydrogen is the lightest atom, it's the best at this. And industrial fermentation is just full of
Hydrogen transfer reactions.
everywhere.
Mm.
Moving hydrogen atoms around is how cells move energy. It's how they break down sugar. It's fundamental to everything.
So the theory is, if we can get enzymes to encourage this tunneling, the reactions happen faster than classical physics says they should. We break that kinetic speed limit.
That is the core of quantum fermentation. Not magic, just subatomic engineering.
Okay, but does the enzyme just sit there and kind of hope tunneling happens? Or is it an active player in this?
That's a crucial point, and it's where the biology is so elegant. The enzyme is not a static rock. The source talks a lot about protein dynamics.
It moves.
It's constantly moving. It breathes. It vibrates. Now think about that barrier, the hill. The chance of tunneling depends almost entirely on the width of that barrier. The distance from where the hydrogen starts to where it needs to go.
If the wall is thick, you can't get through.
Right. But if the wall gets thin, the probability of tunneling just spikes exponentially. So these enzymes seem to gate or squeeze the active site. They use their own natural vibrations to momentarily compress the reaction.
They actually squish the two molecules closer together.
For a femtosecond, yes. They make the wall thinner, creating the perfect geometry for the hydrogen to just pop through.
That is wild. The enzyme is physically manipulating the probability of a quantum event happening.
It is. It's often taught as induced fit, but when you look at it through this lens, it's all about minimizing that barrier width. It's engineering the space to let the physics happen.
Okay, I have to be the skeptic again. It sounds amazing, but how do we know this is happening? How can we be sure it's not just, really fast classical chemistry?
That's the trillion-dollar question. You can't just shout quantum and walk away. You need proof. And the smoking gun is something called kinetic isotope effects.
Keys.
Exactly, PEs. So hydrogen has a heavier sibling, deuterium. Chemically, it's identical. Same proton, same electron. It fits in the enzyme the same way. But it has a neutron.
Which makes it twice as heavy.
Right, like a medicine ball versus a basketball. Now, in classical chemistry climbing, the hill making the ball heavier slows the reaction down a little bit, maybe by a factor of 2 or 3.
Okay, a small slowdown. That makes sense.
But in quantum tunneling, mass is everything. Heavier particles have much shorter wavelengths. They're terrible at tunneling. They just can't get through the wall.
So if the reaction depends on tunneling and you swap in the heavy stuff,
the reaction rate crashes.
Yeah.
It doesn't just slow down, it plummets. We're talking factors of 60, 80, even 100 times slower. When you see that massive drop, that's your evidence. That tells you tunneling was doing all the work.
It's like swapping a sprinter's shoes for lead boots. If they were just walking, they slow down a bit. If they were trying to jump a canyon.
They fall. That is a fantastic analogy. That's exactly it. And the sources are really clear. Scientists have to be incredibly rigorous here. There are strict standards for reporting key Is because it's so easy to get it wrong.
You have to rule out everything else.
Everything. Did the pH change? Temperature? You can't be sloppy. It has to be rigorous to be defensible.
Okay, so we have the theory, and we have the proof that nature already does this. Now, the so what part. Can we engineer it?
And this is where we leave the lab and enter, industrial reality.
Because the goal isn't just to publish a paper. It's to make a vat of bacteria produce more biofuel or cheaper insulin.
Exactly. And the proposal is so tempting. Can we build quantum superenzymes? Can we mutate an enzyme to pack tighter, narrow that barrier, and just supercharge the tunneling?
Sounds like a solid plan. Squeeze it, get more tunneling, get more product. Why aren't we doing it already?
Because biology is never that simple.
There's always a catch.
Always. The commentary in our source basically throws a bucket of cold water on this idea as a magic bullet. The first constraint is the trade-off between stability and activity.
Meaning what?
Well, if you engineer an enzyme to be super packed and tight to force that tunneling, it might lose its flexibility.
But we just said it needs to move to work, to breathe.
Exactly. If it's too rigid, it can't open up to let new molecules in. Or worse, it just becomes unstable. In a hot fermentation tank, a super tight protein might just unfold and break.
So you get the world's fastest enzyme for 5 minutes, and then it's useless junk.
Not great for a 3-day fermentation run. And then there's the systems view. Even if you make one enzyme work instantly, a quantum miracle, the cell might not care.
Why wouldn't it care?
The battery. Most of these reactions need a cofactor, like NADH. That's the cell's power source. If the cell can't recharge that battery fast enough, your super enzyme just sits there waiting.
The Ferrari is out of gas.
Precisely. Or toxicity. Speed up one step in a metabolic chain, and you might get a pileup of intermediate chemicals. If the next enzyme down the line can't handle the flood, those intermediates can accumulate and poison the cell.
So you could kill your factory by making one worker too fast.
You create a traffic jam that destroys the city. It's not about tweaking one atom, it's about the whole puzzle.
The source laid this out in a framework I really liked. The 4-layer causality chain. It shows the complexity perfectly.
Yeah, it's like a ladder. Miss one rung and you fall.
So layer 1.
Layer 1 is the quantum layer.
Yeah.
The tunneling probability itself, pure physics.
Layer 2.
The microenvironment, the shape of the active site down at the angstrom scale, is the geometry right for the jump.
Layer 3.
Protein dynamics, the nanometer scale. Does the protein actually move and squeeze correctly without breaking?
And finally, layer 4, the big one.
The cell or process layer, the macro scale. Does the tank actually produce more stuff, or did you just shift the bottleneck somewhere else entirely?
That really puts it in perspective. You can't just be a quantum physicist or a biologist. You have to be a systems engineer.
That's it. A quantum improvement at layer 1 can be totally erased by a failure at layer 4. If you don't align all 4, you get nothing.
So what's the future then? Is quantum fermentation actually going to happen, or is it going to stay a cool lab curiosity?
The source is cautiously optimistic. It emphasizes that this is a falsifiable scientific program.
Which is high praise in science.
It is. It means it's not just philosophy. We can test it. We can design experiments, run the Chi tests, fail, learn, and try again. It moves it from what if to let's try.
So it's not just musing.
No, but we're not there yet. There's no software pipeline where you plug in an enzyme and get a quantum optimized version out. That's the frontier. That's the work for the next decade.
It's fascinating. We think of biology as squishy and physics as hard math, but here they are, shaking hands inside a yeast cell.
And that's what I love about this. Nature doesn't care about our academic departments. It just uses whatever works. If tunneling is more efficient, nature will find a way to use it.
So as we wrap up, we've learned that quantum fermentation isn't about telepathic microbes. It's about the rigorous subatomic engineering of hydrogen transfer.
And checking your work with heavy isotopes so you don't fool yourself.
Right. But I want to leave you with this final thought. We've been talking about making enzymes a little better. But if we can truly master this, if we can engineer enzymes to exploit quantum tunneling on demand, think about what we're actually doing.
We're not just farming biology anymore.
No. We are designing atomic-scale particle accelerators inside living cells. We're manipulating the fundamental laws of physics probability waves, tunneling barriers to make better beer or cheaper medicine.
It completely changes the definition of bioengineering.
It really does. And if we can break the kinetic ceiling there, What other biological limits are just waiting for a quantum crowbar? If we can hack the physics of the atom inside a cell, what else can we change?
Now, that is a question worth pondering.
Thanks for diving deep with us today.
Always a pleasure.
Hi there, thank you for staying with me until the very end. If these technical insights help bridge the gap in your own process, please hit subscribe and make sure to hit the notification bell. Stay connected for our next deep dive into the realities of biomanufacturing. I am Prasad Ernala. Thanks for listening.